Hey there, Joe here, bringing you a video on rotational kinetic energy. So what we're going to talk about today is the equation associated with rotational kinetic energy. We're going to do an introduction on a concept called the moment of inertia, and then we'll do a quick derivation of the units associated with the moment of inertia. To dive right in, there's two types of kinetic energy. We have the rotational kinetic energy and the translational kinetic energy. So up until this point, we've been talking about translational kinetic energy, which is something moving through space. But an object can also have something called rotational kinetic energy, which is when it is rotating. So an object can have rotational kinetic energy without having translational kinetic energy, like something that's just staying in space and spinning. Or it could, like a ball that's rolling along, have both rotational and translational kinetic energy. So its total kinetic energy would be the sum of its rotational kinetic energy and its translational kinetic energy. So very much like the equation for translational kinetic energy, which is 1/2 times the mass times the speed squared. The equation for the rotational kinetic energy is going to be 1/2 times this thing, which is called the moment of inertia, which is basically the rotational mass times the rotational velocity or the rotational speed squared. So 1/2 I omega squared is 1/2 times the moment of inertia times the rotational speed squared. And so we've already talked about rotational speed. Now let's talk a little bit more about what we mean when we say moment of inertia, which is basically, we can think about the moment of inertia as the angular or rotational mass. So what the heck do I mean when I say rotational mass? Well, to help us think about that, let's think about an egg carton. And this is something that you can try at home if you happen to have an egg carton around. Just make sure you're being very careful with those eggs. So if we take an egg carton on the left and we take the eggs and we put them in the farthest out little compartments versus a separate egg carton where we take the eggs and we put it in the farthest in compartment, and then we try to rotate both of those egg cartons, you'll notice that it feels different when you're trying to rotate them. And specifically, when we're talking about this rotation, we can have different axes of rotation. So what I'm talking about is if we rotate it kind of around the center, it would feel different to have the eggs very far away from the center versus very close to the center. And specifically, I think, and you can test me on this, but I think the one over on the left would be harder to rotate than the one over on the right, just in terms of how much force or rotational force, aka torque, you'd have to do to get it to rotate. However, we could then try to rotate it along a different axis and see if that changes how hard or easy it is to rotate. And actually, in this circumstance, I would suggest that it might be equally difficult to rotate the one over on the left versus the one over on the right if we try to spin it along the long end versus the short end. So anyway, that's just kind of a way to start thinking about the moment of inertia. And something that hopefully you can find something around that you can test and feel the moment of inertia for yourself. Because it's one thing to just listen to me talk about it, but it's another thing to go and try something and try to feel it for yourself. So I invite you to go and try to do that. So different axes of rotation and different orientation of the masses can give different moments of inertia, which basically just means some of them are going to be easier to rotate, some of them are going to be harder to rotate, even though the mass of the box on the left is the same as the mass of the box on the right. Its rotational mass is different based on the orientation of that mass in relation to the axis of rotation. So that was all a little bit complicated, but it gives you a little bit of an idea of the concept of moment of inertia before we dive into the actual equation for moment of inertia, which gets me to the next thing. The equation for moment of inertia is, you'll remember that when we found the center of mass, we took the mass and multiplied by the position of that mass, and we added up all of those products. We're going to do basically exactly the same thing with the moment of inertia, but instead of taking the position of the mass and multiplying it by how much mass is there, we're going to take how much mass is there and multiply by the position of that mass squared. And when I say the position of the mass, I really mean how far it is away from the axis of rotation. So in the previous example, the two eggs over on the left are going to be very far from the axis of rotation, whereas the two eggs on the right are going to be pretty close to the axis of rotation. So their r squared on the left is going to be a big r squared, and on the right is going to be a small r squared. And we're going to take all those products, the mass times the distance from the axis of rotation squared. We're going to add up all of those products, and that's going to give us the moment of inertia. Now that works if we have like 4 distinct eggs, and we can add up each of the mr squareds. But if we have like a rod that is continuous, we're going to have to break that rod into an infinite number of infinitely small chunks. And that gets us right back to where we were for the equation for center of mass. But this time, instead of x dx or x dm, we have r squared dm, or you could think about this as x squared dm. So it's so much like the center of mass equation, except instead of having x inside the equation, we now have x squared or r squared. You can use those two interchangeably as long as you remember x or r is the distance from the axis of rotation. So with this equation, you should actually be able to attempt the homework problems, because in the homework problems, I'm asking you to try to determine the moment of inertia of different shapes using this equation and what we've talked about previously for determining the center of mass of rods of uniform density. So what I want you to do is I want you to look back at your notes from the center of mass, the continuous center of mass lesson, and see if you could apply those notes. Now, instead of using x dm, you use x squared dm, and see if you can derive some of those moments of inertia. And if you get stuck, if it doesn't end up working out, we are going to go over that in our next class. But I wanted to give you some time to try to figure it out on your own, because I don't want to take away kind of the joy of discovery from you. So use this equation and what you know, and I think you should be able to take a dent out of the homework. The last thing before I sign off is you might be wondering, well, what are the units of this moment of inertia thing? Because it's a totally new concept, and I want to know what the units are. And that's an excellent question. So I'm going to very quickly show you what the units have to be. You could look at the equation and think what the units might be, just depending on the product that we're doing here. But let's talk about what the units have to be in order for this equation to work out. Because on the left side, we still want the energy to be in joules. And then on the right side, 1/2 obviously doesn't have a unit. It's just a number. And so I have that blank parentheses there to try to figure out what the unit of the moment of inertia is, in order for when we take that and multiply by radians per second whole quantity squared, we need to end up with joules. So to try to solve for what the units of the moment of inertia must be, first of all, I'm going to do two things. I'm going to say that I know a joule is equal to a Newton times a meter. And then I'm going to distribute that square to the top and bottom just to make the math work out a little bit easier in a minute. Next thing I'm going to do is I'm going to change out for a Newton. I'm going to change that into, since force is mass times acceleration, I'm going to change that into a kilogram times meter per second squared. And then it's a Newton times a meter. So over on the left, I have a Newton times a meter. And then I can do a little bit of simplification, because I have a second squared on the left side of my equation, a second squared on the right side of my equation. So I'm trying to solve for what goes in those blank parentheses. I can get rid of the s squared on the left, s squared on the right, and I'm left with this. But radians, just in the way that they were defined, in the way that radians exist, those are unitless themselves. So we can clean up the right side of the equation to just be the units of the moment of inertia. So through this, we get to the moment of inertia. The units of moment of inertia are kilograms times meters squared, which A, just kind of makes the equation work out to give us joules over on the left side. But B, hopefully makes sense, because when we're finding the moment of inertia, we're taking a mass and multiplying by how far it is from the axis of rotation squared. So kilograms times meters squared hopefully does make sense for the units of moment of inertia. So like I said, this was just a quick introductory video. I'm hoping that you are able to use what we talked about as a jumping off point to start the homework, which is just the beginning of a conversation that we're going to continue next class. But for now, this is Joe signing off of the video of rotational kinetic energy, and go Bugs.